So, welcome everybody to the inaugural Blue Skies Greener Future webinar, which is going to be given today by John Provis. Before we start, I'd like to just introduce a little bit about our network, which is the host organization for John's lecture today. We are the Transforming the Foundation Industries Network Plus. It's a new grant that has been given to the universities of Sheffield, Manchester, Swansea and Leeds. It's based at Sheffield. And we have a vision to engage with academia, industry, policymakers, non-government organizations to develop and adopt transformative technologies, business models, working practices within the foundation industries. There's quite a lot of scope in what we're going to do, and the Blue Skies Greener Future webinar series represents one aspect, and its focus is going to be on pretty much what it says, which is ideas that are transformative and disruptive, that are worth considering for the future within the foundation industry. The TFI Network Plus team is myself, PI at Sheffield, my deputy, Susan, at Leeds, William at Manchester, Cameron, Swansea, our chair of our industrial liaison committee or industrial advisory panel is McDonald. Deborah is the marketing officer, Neil, the network manager. So that's the Network Plus team. And today's lecture from John fits into one of our major themes, which is to look at next generation processes and concepts that could influence the foundation industries. If I go to a more succinct description of what we're going to try and achieve with the Skies in the Future webinar series, topics of transformation and innovation within the foundation industries. We're going to have a lecture each month. We'll probably have a break over summer that will start again in the autumn. Each speaker is a genuine world leader. I'm not just blowing smoke there. John is a real world leader in cement research and technology, who's at the University of Sheffield. And each of those leading speakers is going to present some potential transformative aspects for the foundation industry. And it's blue skies. It's not something you might consider to introduce tomorrow, but it is something that is worth considering for the future and could be absolutely game changing. And that's the purpose of these webinars, starting with John's talk today. I'll let John introduce his title, but I will, as is customary, introduce the speaker himself. You can read what I've written here. I've stolen this from his webpage, so I think it's reasonably accurate. John is an Australian, or has an Australian background. He got his degree, chemical engineering or applied mathematics from the University of Melbourne. Disappointingly in 2002, I think my degree was significantly before 2002. His PhD was in chemical engineering at the same institute. He did research at the University of Melbourne before joining the University of Sheffield as a chair in cement material science and engineering. And in my head, he is Mr. Cement. To me, he's the world's leading person in innovative cement technology. His main focus is on geopolymers, and he'll discuss those, I'm sure, during the talk today. And he has many awards, a ridiculously high number of citations, and he is, without doubt, the leading light, certainly in the UK and probably the world in this field. So it's with great pleasure that I'm going to hand over to John to both introduce his talk and to deliver what I hope is what I know will be an exciting lecture on his research. So over to you, John. I'm going to stop sharing now.
All right. Thank you very much, Ian, for the very kind and very generous introduction, I should say. I'll get my slides up on here now. Share that one, and that should be coming through. So, can someone please confirm that that's come through okay on the share?
I'm good, John. I can see it.
Excellent. Thank you very much. So I'm going to speak relatively briefly today about innovation in cements and concrete, and particularly looking at the question, can we meet future construction needs sustainably? So there's some, let's say, some broader context around how we look at construction and the material we use in construction to try to answer this question in what has to become a much more cross-disciplinary manner. So instinctively, people think when you hear cement and concrete, you think civil engineering, and very rightly so. Notice I'm actually in the Department of Materials Science and Engineering, and as Ian mentioned, having trained as a chemical engineer. So I come from outside the core disciplines of the people who are known for using cement and concrete. And I would encourage those others who are outside the core disciplines that use cement and concrete to think, really, these are much more interesting materials than people give them credit for, much more important materials than people give them credit for. And in a lot of ways, our modern society won't work without them. So when I ask the question, can we meet future construction needs sustainably? There is only one possible answer to that question, and that answer is yes, we must. Because we must meet the needs, and we must do it sustainably, because there is actually no other option for society to continue. So, how are we going to do this? I would contend that cements are in some ways the basis of modern society. We use more cement than anything else in the world except water. The planet produces about as much cement as food every day when we're talking about industrialized processes. Global cement production is 3.8 billion, nearing 4 billion tons a year. So if you multiply that out by the number of days in the year, divide that up by the number of people on the planet, you come up with a figure of about 3/4 of a kilogram of cement per person per day. It's a really important material for global society. Housing, infrastructure, energy generation, transport would all be very difficult or impossible without concrete and mortar that we make from cement. So, and for those who are from outside the core construction materials field, just to introduce very quickly the jargon that I'm going to use here. Cement is the grey powdery stuff. Mortar is, as in bricks and mortar, it's what you get when you mix cement together with sand and water. And concrete is when you've got big rocks in it as well. So when I talk about cement, that's just the powder. When I talk about concrete, that's what you build buildings out of. They've got big rocks in the mix as well. As a sideline on that, every time you see, oh, there's a cement mixer truck driving down the road, no, it's a concrete mixer truck. It's mixing concrete. So when I talk about concrete, that's kind of the finished product. When I talk about cement, that's the powdery stuff. We blend cement with supplementary cementitious materials very extensively. It's increasingly rare to find cements sold and used commercially that are not blended with some form of supplementary cementitious material when we're applying these in concrete. So we blend with blast furnace slag. And actually the construction sector is, in a lot of countries, pays about the same amount of money for ground granulated blast furnace slag as it does for Portland cement on a per ton basis. It's an additive that improves the performance of our material significantly. Fly ash, the ash captured from the chimneys of coal-fired power stations, again, incredibly valuable, blended in as a supplementary cementitious material. The cement sector overall is a net consumer of solid wastes to a very, very large degree. There's gaseous waste emissions, and I'll come back to that. But as a part of a circular economy, cement production is consuming, and concrete production even more so, consuming these very high volume waste materials from other industries. Actually, we run into problems sometimes because we start to run out of other people's garbage. We start to run out of supplementary cementitious materials in certain forms in certain parts of the world. Need to find alternatives. And that's a challenge for the sector moving forward, how we can actually meet our materials needs. Portland cement, we think of as, oh, that's a cement factory I'm driving past. That's grey, that's ugly, that's dirty, that's clearly outmoded. Portland cement is actually a precision engineered product. Portland cement as a material is an engineered combination of at least 5 different mineral phases. Sometimes you get some additional ones to go up to 6 or 7 that become important. Ground to particle size distribution gives the exact strength development profiles you need. The different ratios of the mineral constituents balanced to give you what you're looking for in terms of early age properties in the fluid state and in the hardened state. And despite all of this, it's amazingly robust. Maybe because of this, it's incredibly robust. If you mix cement with, let's say, 50% less water than you really should have, it still mostly more or less works. Mix it with 50% more water than you really should have, and still, again, it more or less works. If you get the mixed proportions in your concrete wrong by surprisingly large amounts, you can still get a material that goes hard. You can use it under quite a wide range of ambient temperatures. You can use it in processes anywhere from highly controlled factory processes to slopping it into a wheelbarrow with a shovel. Very, very few other engineering materials have this range of robustness, this versatility. And it's not appreciated anywhere near as much as it should be. In all of this, we look at the CO2 footprint of sector-wide about 3 gigatons per annum. As an approximate number, producing a ton of cement releases about 0.8 tons of CO2. Half of that comes from decomposing limestone, calcium carbonate to calcium oxide as one of the, well, as the major constituent that goes in to form the 5 mineral phases that I was talking about. And part of the rest comes from the fuel that we need to run that reaction at about 1450 degrees Celsius. So it's largely a fossil fueled process, and it is intrinsically dependent on a carbonate raw material that we're releasing CO2 from. So this high CO2 footprint is driving the search for alternatives. The processes themselves that are running are not inefficient processes. They can't afford to be. You can't afford to produce 4 billion tons a year of material while burning your fuel inefficiently. So we don't. A modern cement plant is, depending the way you measure exact efficiency values, you can argue it's approximately as efficient as a Formula One drivetrain. So it's an industry that knows what it's doing and does it well. So as we're looking to move forward, there's a lot of discussion of alternative cements, innovation in cements, innovation in moving the material science forward and how to use materials better or use different materials to fill this role. So we look for credible alternatives. And a credible alternative, as we're discussing this, needs to be similarly robust and probably more importantly, cheap. Talk about all these wonderful things that cement can do. And most parts of the world, whether you're talking currency units being dollars, pounds, or euros, about 100 currency units per ton is a ballpark figure for how much people are willing to pay for this. So it's cheap as well. So a modern wonder material. I describe it as one of the closest things to magic the human race has managed to come up with. And I say this not understanding how magnets work. They're magic as well, by the way. Cement is a magic material and we can't lose sight of that. So if we look at where we are now, what's our current status as we are assessing the CO2 footprint, assessing the emissions footprint overall of the built environment, which is where we use most of our cement. By the way, it's roughly a 3-way split as we're using cement between reinforced concrete, so concrete with steel in it, unreinforced concrete, concrete blocks, concrete bricks, paving stones, tiles, these types of things, and mortars, renders, and other products that aren't concrete. Roughly split cement production 3 ways worldwide between those 3 categories. If we look at the building stock, you can see greenhouse gas emissions per building for a new construction, the construction and maintenance segment of that. I'll pull up the laser pointer so I can wave at some of these things. So the construction and maintenance section of the building breaks down into all the bits and pieces that go into it. Concrete is that slice, and there are various contributions to 1 cubic meter of concrete, the CO2 footprint of that. And then you take cement, being by far the largest component of that, and break that down into actually where are the emissions coming from in producing cement itself. By the way, these figures come from a paper that we developed through a United Nations Environment Working Group on low carbon cement and concrete. If anyone would like a copy of this, please drop me an email. I know not everyone subscribes to this. It's quite a new Nature journal, Nature Publishing Group journal, Nature Reviews Earth and Environment. I'm happy to email out copies of this upon request. So there are many, many things that contribute to the CO2 footprint of, let's say, our functional unit being the global built environment, or a building, or a cubic meter of concrete. By the way, cubic meter of concrete is not a great functional unit to use, because better concrete you need less of. So a cubic meter of high quality concrete against low quality concrete is a very different functional unit. We need to look at functionality at the element or building scale to really understand this. So as we're looking at the different steps in this value chain, as we're trying to innovate sustainably, the question is, how can we use everything we know here to develop a value chain that works sustainably? There are many points in this value chain that we can attack for this. Where we need to get to, well, by 2050, we've got a legally binding target for net zero. So that's unquestionable. We need to do that. The large process facilities that are producing cement, and a medium-sized cement plant is in the hundreds of thousands of tons per year throughput scale, which is absolutely mind-boggling to those involved in most process industries to think about processing multiple hundred thousands of tons per year of a powder product. These facilities are capital intense. They're designed to operate for 40 years or more. There are cement plants in the UK that have been operating for more than 90 years, replacing, retrofitting, reinstalling new equipment on the sites. But equipment that was installed in 2010 will still be operating in 2050. So is it already too late to fix the problem? Well, it can't be. To some degree, it is. To some degree, the carbon emissions are already locked in from this equipment because value on the assets has to be returned. But we can't possibly let this restrict what we're doing. What we need to improve is every step in our value chain. We need to improve how we use concrete in structures. We need to design better. We need to improve how we use cement in concrete. We need more efficient materials usage to go into that structural design. And we need to better use materials to make cement. So we need to find a way to make cement that is chemically efficient, that has a lower chemical CO2 footprint. We then need to use that cement better to make better concrete, or the right concrete. And we then need to use those concretes better at a structural level. So many opportunities, but if any one step in this value chain breaks down, the whole thing can fall over. But where are the opportunities to improve? This is a graphic and an illustration from that paper I mentioned before. Going from raw material extraction through to building use, demolition, recycling, recycled aggregates going back in, replacing part of the material in the concrete, and using alternative fuels. A cement kiln is an incredibly effective waste incinerator. Looking at alternative raw materials, looking at blending with all sorts of different things. There are opportunities everywhere. And what we need to do is to exercise the right opportunities. So here's some assessment that we looked at with designing buildings better. So designing for reuse, or designing each element of a construction using different concretes more flexibly, and maybe using precast elements more flexibly, design each part of a building to withstand the actual type of exposure, environmental exposure, that that piece of the building is going to be exposed to. So current practice in a lot of building design is to use a couple of grades of concrete for the whole building. So say if you're building a high-rise construction, 8 floors above the ground, you've got concrete elements that are designed to withstand the splashing of the salt that's put on the road for de-icing in the winter. Now, if you're splashing 8 floors up, you've done pretty well. That's better than Sheffield traffic will give you. But we need to bring in, even at that design level, more subtlety, more sophistication in choosing and specifying how we're putting together a structure, whether it's doing it from with an integrated structure, whether it's elements that are going to be reused, rather than building a set of shoebox apartments in the city centre and then coming along 20 years later to knock them down and crushing up the concrete into lumps. Even if those lumps are recycled, you've got a concrete that was designed to last maybe 50 to 100 years, and you've demolished it after 20. So those elements can be reused. We can optimize structures, optimize structural design instead of just a rectangular cross-section, something a bit more clever with them. Now, those structural engineering aspects are, I introduced myself as a chemical engineer. I've talked a lot about structural engineering here. I am by no means an expert in structural engineering, nor do I pretend to be. But it's essential for those on the materials design side to think about how exactly we're going to be using the material. So when we look at using cement clinker, so cement clinker being what comes out of the Portland cement kiln before it's ground, we've got as demolition waste a source of raw material that may already be partially or largely decarbonized. It's had the CO2 removed already. But can we reuse demolition material fines as a raw material to make cement? It's limited by the composition of the raw mix, but this does look possible. We need to pack particles together better into concrete. So we look at, as a functional unit for concrete performance, how many kilograms of cement per cubic meter per megapascal of 28-day compressive strength. At the moment, 8 is about the figure we're looking at. Figures of 4 have been demonstrated. So we can get the same performance from the concrete in a normalized manner with half of the cement content by better packing the solid particles we're putting in there so that the aggregates packed together more tightly, still having a flowable material. We can improve the energy efficiency of clinker production. Again, I said that we're already doing pretty well. There's a bit of scope there. By using alternative fuels, we can reduce the attributed CO2 per megajoule that goes into actually producing the kiln. Blending with supplementary cementitious materials, if we can source the materials, we can reduce our clinker content per tonne of cement from a current level of about 770 kilograms of clinker per tonne of cement, but the cement being roughly 77% Portland cement kiln product and 23% gypsum and supplementary materials. We can change that to as low as 150 kilograms of clinker, so 15% Portland cement in a tonne of cementitious material. If we can find the slags, the ashes, the calcined clays, finely ground limestone, all these things that we'd like to blend to reduce the CO2 footprint, to reduce the clinker content of our cement and therefore our concrete. We can look at carbon capture and storage. And there's actually a roadmap, and it's a really interesting read in the UK cement and concrete sector, a roadmap to reach net zero, which leans very, very heavily on carbon capture and storage and requests funding from the government to please support us to achieve this. Now, a cement plant is one of the best places to implement carbon capture and storage if that's what you're looking to do. Very CO2-rich flue gas stream. But there are a lot of technical and techno-economic challenges around carbon capture and storage that need to be solved. My personal opinion is we can't rely on carbon capture and storage to get us where we need to go. I don't think carbon capture and storage will do enough for us that it can be a key pillar of where we're going. I very much hope I'm wrong. I hope that it's a valuable part of our toolkit for carbon reduction, but I don't think we can assume that it will solve as many problems as it's being proposed to solve. Again, for those in the sector, those involved in CCS, please prove me wrong on this. I'd love to see that. We can look at alternative cements. And it is technically possible to produce cement at 0 CO2 attributed emissions. It's not easy. A lot of alternative cements are looking at savings between 20%, 40%, 60%, some up to 80% savings. Now, in most industry sectors, if you say, oh, I've got an option that will save 20% of CO2 emissions sector-wide, you'd be having people bashing your door down. In the cement sector, the tradition is someone launches a cement and says, this is zero carbon. And then it actually turns out it's not quite zero carbon. Oh, it's not zero carbon. You're only saving 60%. You're only saving 50% of the emissions. No, that's good. Not good enough. We're not interested. You said zero. We're only interested in zero. So the bar is set very high for innovators in this area. To some degree, I think that's unfair. We need alternative materials. And I'll go through, in the rest of the presentation, I'll talk through this in quite some, as the main point of focus, largely because it's what I do. So as we are looking at cement now, I've plotted here on a three directional axes: calcium content, alkali content, aluminium content. Portland-based cement sit up in this corner, and they constitute 99-point-something% of all the cements we're using now. There are a whole boatload of other different types of cement that can be used. Some are being used, some are being developed and proposed for use. But we currently look at the world as if Portland cement is our only form of cementing material. The others, in the right conditions, can be fit for purpose, can be robust, can be cheap, can be reliable, and can be very much lower CO2 in the right circumstances. So what we need is a shift in mindset. Instead of asking, can I do this with the material I have? What we need is to ask, do I have the material that will do this best? We have at the moment a single universal cement. In some ways, you can think of this as like a McDonald's solution. You can get the same Big Mac everywhere in the world. You can get the same cement everywhere in the world. And to be frank, I love a Big Mac. One of the things I genuinely missed during being locked down here is the ability to wander up and get a Big Mac. What a guilty pleasure. But one of the reasons for this actually is it's going to be exactly the same every time you have it. And cement is the same. We have a universal answer. Now, if you were to eat a Big Mac every day for the rest of your life, you probably wouldn't die of malnutrition. If you may get bored, you probably wouldn't die of malnutrition. Correspondingly, nobody has ever been sacked for specifying Portland cement to do something. It's rarely the worst answer, but that doesn't mean it's necessarily always the best. So what I'm putting forward here is a toolkit approach, an array of different types of cements that we can choose from, that we can use, that we can select which cement will do this job the best at the lowest CO2 footprint and at an acceptable cost. These are questions that are not often enough asked, and these are questions that need to be asked more often. And I believe they will be as we move forward. Do we want one size fits all? There are drawbacks of one size fits all. I say this as the parent of a 4-year-old who's tried to find one size fits all hats for a 4-year-old. One size does not fit all. We have worldwide, even within the UK, but particularly looking worldwide, differences in climate. So sometimes we need to design cements for freeze-thaw load. Sometimes we need to design for hot, humid marine conditions. Sometimes we need to design for hot, dry marine conditions. Some places have very sulfate-rich soil. Some places have no sulfate in the soil. All of these things are important in how we select our cements. Some countries, their main priority is development. Some countries, the main priority is repair or retrofitting, depending whether the infrastructure is already in place or whether the infrastructure is being developed for the first time. GDP per capita is a moderately terrible proxy for this, but it's not completely wrong in most cases. So we need to ask, actually, what are we trying to do with the material? And critically, we need to ask which mineral resources are available. Cement is a mineral-based material. We use limestone, we use clays, shales, we use some sand, we use all sorts of other things as modifying materials. If we are going to use blast furnace slag, we need to be somewhere where there's iron ore nearby or being imported. If we want to use coal fly ash, we need to be somewhere where there's coal nearby. or being imported. So we need to understand the mineral resources that are available. There's been some discussion that one of the limitations on development in India in the coming decades may actually be the Indian subcontinent running out of usable high-grade sources of limestone to make Portland cement out of. You don't think of limestone as being a limited resource, something that you're going to run out of anytime soon. But we need to consider this. So I talk a lot about action, and this is one of the classes of innovative cement that we look at. One of the big classes that we look at is alkali activated cements. And it starts from the starting point of, we've got these high volume, widely understood, widely recognized mineral powders that we blend with Portland cement, that we call supplementary cementitious materials. And if we would just mix these with water, they react a bit too slowly to be useful. They're diverse materials, mostly aluminosilicates, and they react with Portland cement because the Portland cement increases the pH up to pH 12, 12.5, 13 in a hydrating Portland cement. Very caustic environment within a reacting cement. That elevated pH starts the reaction of these supplementary cementitious materials. They contribute to strength development, microstructural development, and so on. If we just mix them with water, they go too slowly. So we need to activate them chemically. Now, in Portland cement blends, as I mentioned, you can blend very, very high fractions of some of these materials into Portland cement. Actually, in the current European standards, you can blend up to 95% of blast furnace slag into a Portland cement. So you've got a cement that is 95%. That's the extreme end. Let's say 80%. You've got a cement that is 80% made of a supplementary material. Even with fly ash, you got up to 55% blend fractions. And you get a lot of the performance of the cement from this supplementary material. What if we turn the question around? And what if we ask the question as, if I'm starting from a cement that's mostly made of blast furnace slag, what's the best thing I can combine with that to unlock the performance of this slag? Now, in some cases, the answer to that question may actually be the best thing to blend with this is Portland cement. But Portland cement isn't really designed for this. Portland cement is, as I mentioned, it's a blend of 5 minerals. It's clinker minerals and gypsum, blended, balanced into ground to give optimal rheology, reaction processes, and strength development when it's used by itself as a cement. If we're just using that as a way to trigger the reaction of another component, it's not optimal. It's not the best use of this cement that we've spent all our CO2 making. So we're not using our cement optimally, and we're also not using our supplementary powders optimally. So why not design the chemistry that will unlock the reaction of a blast furnace slag or a fly ash or a calcined clay to the greatest extent possible? Reserve our Portland cement, which, as I've said, is a brilliant material. Reserve that for where we need it and get the best value from our supplementary materials by properly unlocking their capabilities using a chemical activation process. So that's the theory. The practice is, someone thought of this in the 1890s, actually did a reasonable job of it. Jasper Whiting, working in Chicago, had access to blast furnace slags. Cements at the time were, I'd say, much more diverse than they are now, particularly in North America, because they were importing a lot of cements from Europe in barrels. So they're trying to find ways to make cements. Turns out he discovered they could use slag to do this, combined with an alkali. Purden in Belgium published this paper in 1940, which is a very nice piece of work, the action of alkalis on blast furnace slag. He named his company after himself, Le Perdue Cement. He named his cement after himself as well. And these buildings that I've got photographs here, these are actually still standing around the Brussels area. So he got into commercial production, but never beyond a few hundred tons scale. Never quite got the capital he needed because there wasn't the impetus from sustainability arguments to scale up. There was never the driver to really kick these things into action. Work in the former Soviet Union, particularly led out of Kiev, but deployed across Russia and some of the Central Asian countries as well. on alkali activation, the materials they call silicate or soil silicates. The driver there was a shortage of Portland cement after World War II. And that led innovation in slag-based and clay-based cements that have gone into some, I'd say, a 14-story building built with unconventional cements. In Australia, been demonstrated at scale, this airport in Queensland, Brisbane West Wellcamp Airport. Calling it Brisbane West is, let's say it's a generous definition of Brisbane. It's a little bit like saying London North Birmingham Airport. It's a long way away from Brisbane, but it's a nice airport. It's in a town called Toowoomba. And all of the concrete work around this airport, except the main runway, because by Australian standards they couldn't, but all of the regular concreting work was done with cement that contained Portland cement. It was done with alkali activated materials. You ask, this material that's got no cement in it, can it do the job? Well, that's conservatively 300 or 400 million pounds, dollars, or euros worth of Boeing 747-8 freighter rolling over it there. The Cathay Pacific clearly think they can trust it, and who am I to question them on this? So innovative cements, alternative materials, can do the job, can be proven and have been proven to do the job. Why are they not in play? Why are they not available? Well, standards haven't existed up until now. 2016, a world-leading performance-based specification was published by the British Standards Institute for alkali-activated cementitious materials and concretes made from them. I was involved in drafting this. It's a really interesting process to draft a standard specification for a new material. There's an open ASTM work item doing something parallel here. The UK one is a specification rather than a standard. The ASTM standard is working its way through the voting processes at the moment. But we're getting the legislative framework in place to be able to produce and sell innovative cements. And this is for the first time in 40 or 50 years that non-Portland cements have been incorporated into standards at this type of scale. The way these materials are validated is essentially you test a candidate concrete. So you make your concrete that you'd like to propose as a candidate, your activated concrete. You do a suite of performance tests in parallel with a Portland cement-based material that complies with the existing British standards for the job you want to do. So it is very much a fit-for-purpose test program. You start with, I have a material here that I know or assume will do the job because the standard tells me I will. I'm going to apply a set of durability tests to this and to my candidate. And if my candidate performs at least as well as the one that I'm assuming is good enough, then my candidate is approved. And it sets a high bar. It's a conservative way to approach a standard because you've got a material that's already got error margins built into its design. And then you say, I have to do better than that. But uptake of this approach by the UK industry is ongoing. It's a big step away from the existing prescriptive standards, where current concrete standards basically say, what are your exposure conditions? What do you want to do? Well, here's a recipe that you're allowed to use. Here are your ingredients that you're allowed to use, and you're allowed to use them in these ratios. Moving towards a performance-based philosophy is a big leap. And I think it's a critically important one as we look at enabling innovation through standardization. As we head towards finishing, a few comments on sustainability, a few comments on how we assess sustainability. There is an enormous diversity of published CO2 savings for alkali-activated binders for all sorts of alternative cements, where you've got published values ranging from 9% to 97% savings. I don't believe the 97%. I think they missed a trick or two in doing that calculation. The 9% saving is actually, I'd say, this is a figure that's often raised as a criticism of all of this work you're putting in for alkali activation. And these people in Australia, these people in southeastern Australia, we've seen this publication that showed that you made it only 9% better. And that's true for their context. They did their calculations correctly, as far as I can tell. But in southeastern Australia, electricity is generated from brown coal, overwhelmingly from brown coal at the time that the study was done a few years ago. Burning brown coal for electricity is a little bit like burning dirt. It's wet, it's low calorific value, and incredibly high CO2 emissions per unit. So if you're moving to, let's say, electrical-based production of the chemical activators to use in a activated cement, and you've got the world's dirtiest electricity, as my home city of Melbourne kind of proudly does, then a calculation like that may work. If you're in a country with a different electricity generation mix, these figures will shift. So to me, a realistic value of CO2 emission savings that are achievable probably sits more like 40 to 80%. If you were to ask me to narrow this down any further on a global context, I would say I flatly refuse to. I'd maybe be willing to give you 45 to 75. But there is no way you can do a percentage saving calculation without knowing the application, the location, the concrete mix design, which baseline you're comparing against. And so if you say, oh, I'm saving X%, X will come with a very large error bound unless it's for a specific case study. If we're using sodium silicate as the most common alkali activator, that contributes about 90% of the CO2 footprint of an alkali activated cement, particularly if it's coming from sodium carbonate from the Solvay process, which is done in Europe, but not in North America because they've got geological resources of sodium carbonate. So same material produced in Europe or North America, wildly different CO2 footprints. So we need to improve the CO2 footprint of the activator itself as well, as part of this improvement at every step of the value chain that I was mentioning. So what do we really need? Well, we can innovate in cements, and we must innovate in cements to get excellent performance, however we choose to define that: strength, durability, sustainability. Most important thing is the right application for the material in the right location to get the material to. Sustainability requires getting it right on every length scale. So those who are involved at a chemical level and those who are involved at a structural level, who come from completely different disciplines and would rarely speak to each other, need to speak to each other. Conservatism is built into all of our standards, and we over-design materials and structures as a result. Is it better to be too durable or not durable enough? Usually it's better to be too durable. But if you're putting a patch in a footpath that you know someone's going to be digging up next year to put another pipe underneath it, don't design that for 100 years. If you're going to be throwing up some student apartments that you know are going to be knocked down in 20 years because they look hideous, again, don't put 100-year service life concrete into those because it costs money and it costs CO2. You need a robust material because we have a precision material with largely non-precision users. As I mentioned, it's mixed in a wheelbarrow with a shovel sometimes, as well as factory production. And we need a material that will account for this. So with that, I've certainly asked more questions than I've answered today, and I hope this is some useful food for thought. I'm happy to take questions. I've seen the chat box flashing a lot as I've been talking, so I assume there's some in there.
Thank you very, very much, John. That was excellent, very informative. If people have questions for John, if you can pop them into the chat and he'll endeavour to answer them. It's the simplest way with so many people on the call today, on the webinar today. I'll start off by asking John do you think this is going to happen? Do you think people are going to listen to you, John? This is always the fundamental question when it comes down to sustainability. I mean,
some already are. Alkali activated cements are being produced, alkali activated cements are being put into concretes by at least one of the world's largest cement and concrete producers already. So Lafarge Holcim sell a green cement, a green concrete range through their ready mix operations, which if you ask them, I did ask them, I was speaking with senior researchers in the company 10 years ago, that this will never happen. This will absolutely never happen. The second last business trip I did last year before lockdown started was to visit the R&D site where they are developing and trialing and have now put into production alkali activated concretes at scale from a major Portland cement manufacturer. There are increasing numbers of projects going on, particularly in the south of England, around the London area, using a lot of alkali activated concretes. And as I mentioned, ASTM are putting a standard in place. I spoke last week at the American Concrete Institute, where they were asking questions around how can we deploy these, again, at scale in North America. So it's happening.
Excellent. That's very good news. There's a couple of questions appeared, at least one question appeared. How much can CO2 uptake by cement during or after normal life be exploited to reduce net CO2 impact? From John Gibbons.
Contentious, depends who you believe. There are a lot of discussions around this. There was a very high-profile paper published in Nature Geoscience. It's 2016 now, so a couple of years ago, where they claimed that over 40% of the chemical CO2 emissions from cement production had already been taken up by concrete in service. Now, I worked through their model in some detail, unpicking what they've done, and some minor catastrophic arithmetic errors aside, I think that figure's more like 11%. So single figure percentages of chemical CO2, and then chemical CO2 is half of the emissions. We can't rely on carbon uptake by cements in service, even if we're crushing down construction demolition waste to very, very fine particles and spreading it out. Because if we're crushing to fine particles, that takes a lot of energy, need a lot of space to spread them in. And the entire principle of Portland cement durability design is to keep out atmospheric CO2 because that's considered to be a method of degradation. So if we are relying on CO2 uptake in hardened materials, undoubtedly it happens. There are European standards in place based on this model I described for how to calculate that in an LCA basis. And I'd say I'm a bit of an outlier among the community, although not entirely isolated in this. I'd say putting a hand up and saying, actually, I think there are enough mistakes in the calculations that underpin some of these models that we need to be more cautious than we are.
Here's a question here from Wakas, who he asked the question a while ago, but if I repeat it again here, he thinks it was an excellent talk. To look for new materials, which method do you see paving the ways for us engineers to reach the decarbonisation targets? DFT, other physical chemistry simulation techniques, or are you banking on scavenging and exploring more remote regions and stretching the periodic table if possible? Quite a question.
What we have to remember as we're designing cements is that we need enormous volumes of things. So cements that are based on exotic elements, yes, you can put things like boron and gallium and all these types of things into cements, and you can make some quite nice cements out of that, and you can make a gram or three of them. Basically, we need geologically highly abundant elements, and that's one of the key limitations. Okay. Scavenging is a very good terminology. We need to identify sources of waste that we can use. We need DFT and physical chemistry techniques at the atomistic level to help us understand what's going on. But cement and concrete performance is really determined at the microstructural level. So on the modeling side, we need to span from that atomistic level through a mesoscale model to understand the microstructural aspects. So DFT work and these types of things are important. It's, I'd say, necessary but not sufficient.
Okay, thank you, John. Cam, forgive me if I pronounce that incorrectly. Wants to know the difference between an alkali activated cement and a geopolymer.
Depends who you ask. If you ask me, geopolymer is a neat marketing name for some types of alkali activated cement. I don't often use the word geopolymer in a scientific context, but it's a word that's been thrown around a lot as a way to market materials. And I prefer to talk about alkali activated fly ash, alkali activated metakaolin, There is debate about some sort of mystical, magical formula for a stoichiometric geopolymer that makes it work better than other formulas do. I don't believe that, and I haven't seen evidence from the proponents of those theories to support their claims. So to me, a geopolymer it's a nice advertising name, but doesn't go any further than that.
Okay, that clarifies something for me as well. I always get confused. I just assume they're kind of all alkali activated. That's the trick. But yeah. So from Theodore, do newer blended cements, CM-2, absorb less CO2 than CM-1, which was mainly used 20 years ago?
Yes, short answer. Slightly longer answer, and this relates back to the CO2 uptake in service. The blended cements have a lower calcium content. The CO2 uptake is reforming the calcium carbonate from calcium silicate hydrates, essentially by degrading the calcium silicate hydrates, or from the portlandite in the CEM1. So CEM1 has a lot more portlandite, more calcium hydroxide, so that can be converted back. The CEM2 and CEM4 and CEM5 cements, particularly CEM3s, the high blend CEM3s, that have got a lot more blending fractions, a lot less calcium in them, and much less portlandite. They will take up less CO2 because they carbonate the portlandite first, and then once the portlandite's carbonated, you have CSH degradation. I see the comment from John Gibbons on published correction on CO2 take-up calculations. That's an interesting one because we sent that to Nature Geoscience, showing they were wrong by a factor of 4. And Nature Geoscience sent that to the authors, had a look at it and said, actually, we don't think this is interesting enough to bother publishing. So we tried to do that, and we'll continue to try to do that, but the journal that published the original mistakes wasn't interested to correct it.
I'm afraid that's a common feature. Being a policeman is never very successful.
No.
So I think we've got time for just one more question because this is scheduled for an hour and people have other things to go to. So I'm just going to pick out one at random. Forgive me if I don't get to your question. There's quite a lot here. Budaoud Mohammed asks, which method is the best to choose? The best kind of activation and ratio for the preparation of geopolymer for natural industrial waste? I guess he's asking about what's the best ratio of your components in your formulations, I suppose.
Honestly, there is no substitution. There's no substitute for laboratory test work. The way to find it is to look at what people have done before with similar materials and blend up a few possibilities using your own materials, identify what's working and refine experimentally. Actually, one of the weaknesses we have, one of the challenges we have is that there's not an easy way to ab initio predict what is going to work for a given source of, let's say, less well characterized raw material. So what you need to do is basically trial some blends, see what works.
Okay, always nice to know that trial and error remains with us, irrespective of how smart we think we are. So just to round up, just to note that our next TFI Network Plus event is going to be our road mapping exercise on the 19th of April, which it's a workshop. We recorded you, invite you to come along to that. The Eventbrite is out already. And this was the inaugural event in our Blue Skies Greener Future webinar series. We'll be continuing the series, as I said in the introduction. The next person talking is actually on quite a related topic, I suppose. And it's going to be Professor Clive Randall speaking about cold sintering in ceramic. So we're following on very much in a low temperature technology, not quite room temperature, but certainly very low in the context of ceramic. And that will be taking place on the 12th of May at 15:30. An Eventbrite will be issued on that. Please register as before. I think after that, we have Mark Rainforth talking about designing alloys for resource efficiency. So we're going over to metals. So we will go through systematically the aspects of the foundation industries, focusing on more disruptive, innovative technologies that should be delivered in order to attain net zero in the coming years. So it remains only to thank John for a hugely informative talk. I certainly learned a lot. I think I knew a little bit of it before, but I certainly knew we have learned significantly more on the talk today. And please, John has limited time at the moment for many, many reasons. But I'm sure, you know, if you asked him nicely, you can send a paper off to us.
Absolutely. Yeah, please drop me an email if you'd like a copy. I'm always happy to send out copies of papers.
Yeah, so you can quickly do that for you. And if you have anything that you want to ask the PFI Network Plus team, contact Neil Lowry and he could let you know any information you need with respect to our overarching organization, the Network Plus. Okay, so thank you very much for attending, and thank you very much, John, for delivering an exceptional lecture. I hope this is the beginning of a wonderful series. It's certainly a fantastic start. And let's hope the other lecturers meet your very high standards that you set today. Thank you very much.